Welcome to my video. So today I would like to show you how I'm performing X-ray diffraction experiment on single crystals at Diamond Light Source. So Diamond Light Source is a synchrotron in the UK, in the Harrow campus, and that's how Diamond looks like. So inside here is a large storage ring that contains electrons that are accelerated to very fast speed, to almost the speed of light, and while they do that, they emit radiation. So while they are being in this large storage ring, radiation is emitted that we use for our experiments. And in our case, we use X-ray diffraction experiments, so we need high energy, high flux X-ray radiation for that. So firstly, before electrons go to the storage ring and they are able to emit radiation, they are created using electron gun. It goes then through the linear accelerator to the so-called booster synchrotron, where the electrons actually reach the proper energy, and then they go to these large storage rings. And these protruding places here are the beamline stations, where we can use the radiation to perform our experiments. So I'm going to use beamline I-19. It's a dedicated beamline for single crystal X-ray diffraction. Generally for small molecules. So I'm going to show you step by step what is happening. Here you can see a view. It's a robotic arm, and here is our detector, and here is the whole goniometer and in general diffractometer. So what's happening is I send samples in cryogenic conditions in DUR of pre-mounted single crystals, and then the robot is able to pick the crystal from the ones that I prepared, mount it on a goniometer head, and then I can do the experiment remotely while I am actually now during a conference in Germany, and I'm able to perform remote experiments that are happening in the UK. Okay, so let's see how it's working. I'm going to go to the system where I'm able to exchange sample. So I'm going to try another sample now. I will load it, and we'll see what's happening. It will take some time, but generally detector will move out. Then the sample which is mounted here, we'll see it in a second on the left side image. Our sample which is mounted somewhere here, we will get rid of it. So the robot will remove the sample first and then put on a new sample. Okay, Mr. Mitsubishi should start working soon. Okay, so you can see that the robot is removing the sample right now. It's taking the old one, putting it back to the DUR with liquid nitrogen, and I'll quickly go to another view. And here is where the robot will mount a new sample. We should see it in a second. Yeah. Boop. And our sample pin is mounted. Cool. I can now go back to our view. And what's going to happen now is the robot, the software, will try to more or less center the sample. We'll see if it manages to do that. Sometimes it fails, but I think it should do a good job here. Yeah, so we can see already sample mounted on the loop moving. Yeah, and we see the crystal here. It's actually not that small. It probably doesn't really need synchrotron, but I have plenty of other samples that really need this radiation. There's a little bit of ice which is formed during this cryogenic transfer to a DUR when I prepare samples, but usually this such small amount of ice is not even meaningful. You probably can't even see it on the diffraction pattern, at least according to what we've seen with these samples. I think, yes, it managed to center the sample. We can just improve the centering just a little bit. It always works better when your sample is at size of the loop. This one is larger, right? So let's try to center it more or less. I'm not going to try to spend too much time on that, as I already have one very good data set from the sample. But we are again manually from Germany centering the crystal that is mounted in the UK, which is quite surreal, right? Okay, so the sample is centered, and now we can load the default run list. I'm going to call this experiment pre, or maybe SCR, like screening. So first we're going to just do simple screening. And the amazing thing about Diamond, and about access to synchrotron, but especially at Diamond it works really well, is we are using the same exposure time. So we are using a 0.1, or later during the actual experiment 0.2 degrees per image. And very low exposure time, so we can see 0.1 or 0.2 seconds per image, okay? Seconds per image. And we are not going to now increase or decrease the exposure time like we would do at the in-house source. What we're going to do is, instead of increasing the exposure time when we want to decide what exposure time to set, we're not going to do that. Instead, at synchrotron, the whole benefit of Diamond is that we can tune intensity of our radiation, of our beam. So the experimental time will remain the same. It's about, together with robotic arm movements, about 15 minutes per sample, which is amazing, right? But now we will tune the intensity of our beam. So during this pre-experiment, I will use only 0.5% of the beam. It will be only 0.5% of the maximum intensity of the beam that we can reach. And I'm going to run it now. And let's see what happens, whether we're going to see some nice diffraction pattern or not. So again, we are only changing the intensity of the beam. It is done by inserting attenuating foils, and we are attenuating it quite a lot. Everything happens by software, right? We just put the value, and we are only going to use 0.5% of the beam, and it might be that it will be even too much, but we'll see. The software will later suggest us what exposure to use to not saturate the detector and to get some good, meaningful data that could give us a nice crystal structure. Okay, it always takes some time. I can just show you here. Now there's, in this DOR, there's a refill of liquid nitrogen. It always makes this cloud. It happens every, I don't know, what is it, half an hour, 20 minutes. But at this position, we can see the beam stop here. It should start measuring in a second. Okay, so we can already see that images are being collected. You could view it in a viewer, but we should be able to see some sort of diffraction image here as well. It won't be of very good quality, but we could do that. The problem is that just you don't want to open thousands of windows while we are in this, during this beam time. We have about 100 crystals to measure, so I don't really want to waste time for that. And we should also see it in our processing website. That's the old crystal, I think. No, that's the crystal. So you can see that the diffraction pattern is nice, strong. We can see nice diffraction spots. So yeah, looks pretty good. Let's have a look what's happening in the meantime with the processing software, because the processing software will show us soon some statistics, and based on these statistics we'll be able to decide what exposure time to, sorry, not exposure time, what intensity, what attenuation to use for the actual data collection. Now we are only collecting a pre-experiment. This sample is a bit tricky. I can't show you crystal structure of this one, as firstly it's not mine, it's from someone in my lab, but it's also, let's say, a top secret sample. But if processing works automatically, and it doesn't work here, there's probably some issue with the data, but it should in general show you a solved structure already here. So this whole website is just amazing. We can view everything in real time. We can see how software processes the data. And then if we have a twin or something is wrong, we can expect the data, for example, in Chrysalis. Okay, so we have some information. So here we can see that we are hitting about 40% of the maximum detector intensity. It is recommended to put it below 25%. So now we're doing some maths. If we are using 0.5% intensity of the beam and we are getting about 45% and we want to go somewhere below 25, how much do we have to decrease the beam intensity? Well, we can probably do it by half, right? And I will actually put it slightly less. Sorry, that's the camera. So for the actual experiment, I will use 0.2% of the beam intensity. Okay, now I'll just change the name to col1, like proper data collection for the sample number 1. I'll select these runs for the proper experiment and I'm gonna run it. Okay, so I hope that was exciting for you to see what's happening with this robot and how to set up a diffraction experiment at I-19 beamline at diamond light source. And in the next video, I will try to show you how the data processing works and how we are getting the final crystal structure from our beam time. Thank you so much.